Hello, geometry. Today we are doing some work with radicals because we are going to start analyzing some right triangles in this section. So I'm going to start with, first of all, this symbol is called the radical symbol. We often call it the root symbol because it's square rooting, but it also cube roots or does to the fourth root. The number inside is called the radicand. So we've got the radical and the radicand. When it's just like this with no number, it's always a hidden 2, meaning we're taking something that multiplies by itself twice to equal 7. Whereas if maybe it was that, we're having a cubed root, so it would be 2 times 2 times 2 equals 8. And you can do fourth roots, like 81 is a fourth root. 3 times 3 times 3 times 3. You can do any number of roots. If there's nothing listed, it's a 2. Okay, we're going to do simplifying radicals first. So if you had like the square root of, I don't know, 40, that can be listed in more simple terms. So to start with simplifying radicals, we're going to make a factor tree. Okay, you remember this from 6th grade-ish. What two numbers multiply to equal 40? That would be 2 and 20. 2 is now a prime number, so we can stop there. What two numbers multiply to equal 20? 2 and 10. Can't divide anything into 2. And then we have 2 and 5. And now none of our numbers can be broken up. The only thing that multiplies to equal them is themselves and 1. So 40 is the same as 2 times 2 times 2 times 5. And since we're to take the root of 40, we're going to take the square root of those. Well, 2 times 2 is 4. And we know that the square root of 4 is 2. So when things happen in a pair, they get to come outside of the radical. Because 2 times 2 is 4 and the square root of 4 is 2. It cancels each other out. The 2 and the 5, they don't have buddies. They can't get out. So they stay in. So the 2 times 5 becomes a 10. And we have 2 root 10. So that is now square root of 40 in simplest form. Let's take another one, like 120. Okay, break it down. 2 times 60. You don't have to break it into 2s. You can break it into any two numbers. 2 and 30. So I could do like 3 and 10. And then 2 and 5. Okay, so I'm looking for pairs. I've got 2 2s. And then the 2, the 3, and the 5 have to stay inside. So the 2's get to come out because they had a pair. 2 times 3 times 5 stays inside, so that's 30. So we've got 2 root 30. What if we did something like 32? 4 and 8. And then we've got 2 and 2. 2 and 4, 2 and 2. Okay, lots of 2's. Pairs only. So these 2's can come out. These 2's can come out. And that 2 has to stay in. Notice we're not doing anything with the 4, the 8, or the 4. They've been broken down, so they don't really exist anymore. 32 is 2 times 2. 2 times 2 times 2 times 2 times 2. Okay, so we had 2 sets of 2's that were able to come out. And then 1 2 had to stay in. So the square root of 32 simplified is 4 root 2. All right, I'm going to show you multiplying and dividing radicals. And it works exactly like multiplying and dividing variables. So if you had something like 3x times 5x times 2y, you get to multiply the like terms together, and that's it. You multiply the like terms together. So the 3, the 5, and the 2, those are all like terms. So they're going to go together as a 30. The x's are like terms. So they go together with an x squared, and then poor old y, he's not like anybody, he stays by himself. If they're like terms, we can multiply them together. Same thing if we're doing division. If you have something like 6x to the 4th y squared divided by 3xy, you're only really dividing the like terms at a time. You're going to do the 6 divided by the 3, and you're left with 2. You're going to do x fourth divided by x, which is x to the 3rd, and y squared divided by y is y. So again, you're dividing like terms. So when you're doing radicals, so if you had like 2 root 3 times 3 root 5, you're going to multiply like things. The 2 and the 3, they go together. That's 6. And then the root 3 and the root 5 can be multiplied together to be root 15. And then you might have to simplify that root 15 if necessary. If you're dividing roots, so like 6 root 7 divided by 3 root 3, it kind of happens the same way. The 6 divided by the 3 is 2, and then the roots can come together, and this is actually 7 divided by 3. So you divide what's under the root, just like you over here, we've multiplied what was under the root. Okay. And then we have adding and subtracting. And it again works a lot like variables. Like if we have something like 3x squared plus 2x, we can't add those because they're not exactly the same variable right here. If I add another one like 5x, these two can come together. So we get 3x squared plus 7x. But that's as far as it goes. I had 2y cubed minus 2y squared plus 3y. None of those terms are exactly alike. They can't be added. Y cubes, y squared, and y's aren't the same thing. We get cubes, squares, and singles. They don't go together. Radicals are kind of the same way. So we had 3 root 2 plus 5 root 6. That's as far as that goes. This cannot be simplified. If I add something with the exact same radical, like 8 root 2, those two can come together. They are like terms. So that would be 11 root 2's plus 5 root 6's. All right, so when you're adding and subtracting them, they have to be exactly the same ending. Last thing we're going to do today is called rationalizing the denominator. And this is something that's really kind of outdated now that we have calculators instead of using these big long books to look up like what the square root of 7 was. But it's still a process that you need to know how to understand. It just doesn't have a true purpose anymore like it used to. So rationalizing the denominator is when you have a radical in the denominator. That's just no good. Because what happened before we had calculators, they would have this. 3 divided by 1 point, this is just an estimate, 1476. And this number was like 8 to 10 digits long, and they had to do this long division style. Can you imagine doing this problem? Yep, nope, me neither. So that's why they rationalize the denominator, because we don't want to divide by this long decimal. So we do what's called rationalizing. which is just the process of getting the radical out. So you're going to take this 3 divided by the square root of 2, and you're going to multiply it by 1. Because when you multiply by 1, it doesn't change anything, right? Exactly. But it's going to be a fancy one. It's not going to be 1 over 1. It's going to be root 2 over root 2. That is still 1. So I'm not changing my value. It's still going to equal 3 divided by root 2. But watch what happens. When you multiply fractions like this, 3 times root 2, now 3 times root 2, and then root 2 times root 2 is root 4, which really just equals 2. So now we have a normal whole number on the bottom, which would be much easier to do if we're doing long division. That is the process of rationalizing. Get rid of the radical in the denominator. So if we had another one like 7 root 3 divided by root 5. Okay, that root 5 is the problem. Multiply it by your special 1. So the root 5s cancel out. See the bottom first, we got root 5 times root 5, which is root 25, and that simplifies to plain old 5. And then at the top, we're going to do 7, and the root 3 and the root 5 we're multiplying so they can go together, and they will be root 15. Now the 15 and the 5, they don't simplify because they're not like terms. It's root 15 and a 5. They're not the same, and 15 can't be simplified either. So that is your final answer, 7 root 15. All right, now, if any of these sections are confusing as you're working on your worksheet today, there are a billion good YouTube videos out there. Just type in rationalizing the denominator and they'll focus on this, or multiplying radicals. Okay? So work on that worksheet that should be attached for today, and I'll see you the last 10 minutes of class.